Hello. Oops. Can you hear me? Can everybody hear me? Oops. Oops. Do you get audio? Yes. Okay, great. So we're waiting for the rest of the students. They are a little bit late. We're also having a problem with the wireless. Okay, so I'm gonna mute for the moment.
Hello? Hello? Hello?
Yeah. Hi, this is Sam Croker.
Hi, this is Tom Whalen.
Yes. Hi.
I was going to use the by computer, but I couldn't find a place to type in that I was even here, so I switched to telephone, although I hate to tie the family phone up for 2 hours. I'm going to switch over to headphone. Okay. Can you hear me now? Can you hear me now?
I can hear you.
Okay.
So let me see. Well, I'm connected. Let me see. Okay, yeah, maybe. Yeah. I can read the key.
Oh, it's the key. It's over there. I put it over there. Yeah. So if you need wireless access, the key is over there. Okay. So let's wait another 4 or 5 minutes. Mm-hmm. Hmm?
Use that one as well.
Yeah. Thank you very much. 1, 2, 1, 2, 1, 2. It's P. Either you should use the PXLB guest 2. It's closer. So you're all gonna be there, okay, same computer. Okay, that's fine. It might actually work better having more than one people on the same machine. Like that's the idea of the course. You know, we want to make it more as a lab session rather than a. Mhm. Mhm. Of the R Hadoop. So we're not gonna need it today, but somebody's painting on my wall. But so which are you using Ubuntu? So I don't think it's gonna run. I'm not sure. I think, correct me if I'm wrong, I think does anybody know if you can have a 64-bit guest on a 32-bit host, Ubuntu? I think, is your machine 64-bit? I think if your machine is natively 64-bit, you can do that. That'll be okay. That's fine. So today, actually, for the remote students, we have how many? 1, 2, 3, 4. It's going to be better because we have this WebEx thing. We got a camera. We got a Wacom tablet to write on the board. So hopefully it's going to, okay, I'm able to connect on the internet. Okay, excellent. Let me have a restart here. Let's see if I can. The truth is that we do have Ethernet cables, but because this is the corporate network, I can't hook you up on this. Meanwhile, you can take a look at these books that I brought here today. This is R in a nutshell book that has a lot of the things that we've been talk about. It doesn't have really extensive information about it, about R, but it's a good reference book. So if you wanna, so this is a classical book for machine learning, the elements of statistical learning. There is a second edition too, and it's free on the web. I think if you go to the class today, I'm kind of like showing pages where you can read about the stuff we're doing today. And this is a very new book. It's called Machine Learning. It's probably the most complete book you can find in machine learning. It has everything. Don't take notes. It's also in the wiki. Like you can find this in the wiki. So let me make sure that there's nobody else waiting, and we'll start now. Side. Okay, so I don't see anybody else coming. So
You're running a Mac, right? You run everything on the Mac? Like R and R stuff? Yeah, I'm actually new to Macs.
okay, so let's start.
You're not doing anything tomorrow, huh?
No, I'm doing tomorrow. It's the second class. This is the same as last Friday. So this is the first class. This is how they call the B series. You know, the A series is on Fridays. The B series is on Thursdays, and we're going to repeat what we did last Friday. Last Friday we forgot to make introductions, so obviously I'm Nick. You probably read about me in the meetup. So let's start with you. Who are you?
Michael.
A little bit because the microphone is here.
Oh yeah, sorry. I'm Michael Galvin, and I work at a software company called TRX. We do mainly travel data.
So you are Raj's friend that I can send? Yeah, that's how I met you, with the nearest neighbors. And I realized we had exchanged some emails while I was in the Fast Lab with Alex Gray. So, okay, who are you? This is second. Oh, I have to. What I guess return. Just a second, we have to mute. Oh, sorry. We've got something playing over here. Okay, so please continue. What's your... Who do you work with? Oh, faculty. Yeah, I know him. And you are?
I'm Moses Sardori. We are in the same class.
Okay, so we got students on Thursdays. And you are? So you're all from signal processing. And you are? Okay, great. So let's put the camera back. So I want you to go to the class wiki and the meetup, and you go where it says lessons overview assignments, and you go to lesson 1. I wonder where's the rest of the people. 14 people registered, and is there traffic outside or anything? So yes, it says lesson 1. So first of all, has everybody installed Hadoop? Oh, here. Okay. Hi. That's okay.
Northeast, northwest. Turns out they're two different.
Hello?
Oh, hello. Yes.
Yes. Well, I got into the Google files, but is that the same thing as Hadoop?
Just a second. So Google Files, what are you talking about? Are you talking about the data set?
Yeah.
So, can you repeat again?
I followed the link for Hadoop, and this is where I ended up.
Where did you end up?
In Google Files. Well, it says
so that's
Meetup, Learning Machine Learning by Example, Pages, Course Data Sets.
It might be a wrong link. I might have made a mistake, but we're not going to need R Hadoop today. We're only going to need R. So you follow the install R Hadoop, follow the instructions here. Yes, and it says installing R Hadoop and R. So were you able to install R?
Well, I have an R installed already on Documents and Settings, and I did a new install directly on the root directory of C. But I haven't done anything but install it.
So yes, all we need. Are you running Linux, Windows?
Windows.
Yeah. To be honest, I don't have that much experience with Windows, but and that's why my advice is also if you can use an Ubuntu VirtualBox, so that we're all in sync. But for the moment, I think if you have a Windows installation, it should be fine. Did you have any problem installing Windows? Installing R on Windows?
No, I've done it successfully before, but I know that the default, which I have, installs it on Documents and Settings, and so you can't do packages. So I've never created a package because I had it on a path that had spaces in it, which is why I started the process of doing an install on.
So unfortunately, I mean, I think if you install R and you open an R command prompt, then you can install packages from there.
Yeah, but you can't create them. You have to be on a path that doesn't have any spaces in it to create them.
Okay, so then why don't you make an installation somewhere where it doesn't have spaces?
Yeah, I just started that today.
Okay.
Didn't get very
So
far.
let me, because I've got some questions. So what is your question? So have you installed R? So you're fine.
Yeah, my confusion is with Hadoop, but you say we're not.
No, forget about Hadoop for the moment. Okay. We're going to install it next time. Okay, so.
Okay.
I've got R installed in Windows and I'll install it on boot type virtual machine.
Okay, that's fine. So what's your name again?
My name's Noir.
Noir. You are the Noir, black. So let me people here. So you are Noir and you are a student? Yes.
I am an eternal student, right? As we all are.
No, eternal student. Okay.
No, I graduated last year and I'm launching a technology company.
You don't want to tell us more about it?
I can tell you more.
Okay.
Go to DC tomorrow.
Is it a security company? Because you said this. Okay. So which, by the way, feel free. I mean, we're working on this data set about the airlines, but if you're welcome to bring your own data set if you want, and start working on that and ask questions. So anyway, so everybody has installed R. I mean, if you have installed R, you can start going to the next one, which is downloading the airline data set. Have you downloaded the airline data set? Everybody?
I've accessed it on Google's files.
Yes, I had to put you don't have to install it everything now because it's a big data set. It might take time. You only need for this assignment something that says it's like under samples 2007-small.csv. Okay, so does everybody have that? Okay. Now, when you go back to your dorm, home, wherever, you can actually install, download the rest because it's about 1.5 gigabytes and it takes time. Okay, so we've done that.
Yeah, well, I haven't, but
take your time. We're going to go slowly. Okay, now open R and load your data. I think I have 1987. Just use a 2007 file. So go to the next.
Okay, I've got the command prompt in ARP console.
Okay, so follow the instructions to load the data.
Okay.
You can access it from the Google. No, there's a small one. Just get the small one. Just a second. No. I have a mirror. I have a Google Drive one. Link for faster download. That's why exactly the ASA whatever website is pretty slow. That's why we're using the other one. So do we have the data loaded?
Okay, I've got something that says, please use this link for faster download, and it brings me into Google Files.
Yes, and from there, download the. And sometimes I don't know if I make sense, but I'm also listening to online students. That's why you don't have that sound there. But yes, so just go to under the directory samples and download the 2007_small. So anybody managed to load the data? We'll take your time. We've got 2 hours. That you don't have to.
Not working.
Yeah, that's exactly what you have to do. Okay. So
samples?
This is under samples. Yes.
Uh-huh.
Yes. If you try the 2000, anybody try the 2007 full?
Okay, here it is down the bottom. 2007 small. Finally found it.
Okay, so if anybody tried the 2007 big, what did you do? You said you tried it and you ran out of. You couldn't even read. How big is the 2007 as a CSV? It's around 700 megabytes. So is that big data? Not very big. It's about 7 million entries, 12 million entries, something like that. So that brings the first debate. What is big data and what's small data? So, it turns out that's like the whole traffic for the United States, all the flights for a year. And it can fit in 700 megabytes. It's pretty small. So externally, it looks like big data. In reality, though, it's not really that big. Despite the fact that it's small, what is 700 megabytes? It can fit, you can probably fit all the data set in your cell phone right now. I think the whole data set is 1.5 gigabytes compressed, maybe 10 gigabytes and 15 gigabytes uncompressed. But this kind of shows you why we want to move to R Hadoop or maybe other solutions, because it turns out that R is very bad with memory and memory management. Even if you were able to load it, you will realize very soon that it becomes very slow. The garbage collector is not that efficient. And I'm negotiating right now an educational license for Revolution Analytics, the RevoScale R, which solves this memory problem. And of course, the other solution is R Hadoop, which is slower than RevoScale R, but it's free. Okay, so hopefully we'll know by the end of this week whether they're going to grant us a license for this course. So you weren't able to load the 2007. Now, did you try to load the 2007 small? I think that's around 10,000, 100,000 entries. Can you check how many entries is the 2007? Just type length and whatever I call it, my data. That's like the command you use in order to find out. Now, was anybody else able to? Okay. No, students from remotely, if you need to post questions, you can either post them on the whiteboard, on the chat. The whiteboard would probably be better because it's visually more stimulating. We'll be able to see it. So anybody managed to run the summary?
I've got it down.
For the small one. Just cancel that and try use the small one. You should use the small. Did you download the small one? Just force close, yeah. Anybody was able to load the small and do the summary? Let me see. Oh, why? Are you loading that from HDFS?
No.
So, okay, you did, it's not length. If you do summary, my data, and that's what you get? Can you check the text file to see how big it is? That's
okay.
Was anybody able to run the summary over the data?
I messed myself up with this by doing this.
Can you open it?
Manipulation.
Okay, so it wasn't loaded properly. Were you able to load it? Anybody from the remote students was able to load it?
Data, import data.
Okay, Jacob, yes, for small one, you were able to load it. For the big one, you're right, it crashes. We explained that. Okay, how do you do CD in R? I think it's, let me see, get CD or something. Yeah, you can. I think it's anybody get. I know you. Is it GCWD? I can't remember right now. I think if you're trying to load the data, you can use the full path. But doesn't it? Let me see. Cause, working. Get. So get WD is the current directory, and then.
Okay, I've got it as one big column comma with the commas still in there.
Okay, set WD, you're right. Get WD and set WD. Right, set WD is changing directory. So, did you try to run the summary? So what did you get? You get something, a list of the name of the variables. So we all understand what the mean and the max are, okay? Then it says what, median? Median. So what is the first, second, third, and fourth quarter? Do you know? So basically it means that, you know, the value you get, 25% of the data is less than this value. The second is like 50%, which is the median, the 75%, and then the 100%. So do you understand that also, remote students, what the quartiles or quantiles mean? Okay, it's very. So what about the destination and origin? What kind? You have the file as one column with a comma still in the one big column. So that's, yes. So just before I answer the student there, what you get for categorical variables, so destination and origin is 129 city codes, just to understand, and it gives you the histogram over this, like how many times in the data set. Can you, so who's, Thomas is posted that on the board. I have the file as one column with a comma still in the one big column. I don't know what you mean by that. If you open it as a CSV, do you see it in columns?
No, I just see it's one column wide, and what's in the column is a text string, which is all the stuff with oh, you're right. You know, all the data is there, but it's
Can you run a summary?
No, because it's just a text string with the numbers as digits separated by columns. I've got it into Excel, and I was going to save the Excel file, and then I know how to import from Excel.
So excuse me, what do you say? How do you? I think you can say data. I mean, if you want to, you can say data as matrix, data.as matrix, and that will give you a matrix, and then you can use commas. But you can access it directly. Let me have my
import data from Excel. Override the name.
You can also, okay, if you also have questions, that's why I have it. You can also consult that book over there as a reference. You know, and I have to be honest with you, my expertise is mostly in machine learning. Typically, I work with other languages. I don't really like R as a language, to be honest. It's a universal language of statistics. But I find C++ and Python, and I don't know what you think about that, more easy to work. The goal of this course is to go through some machine learning concepts. We're using R. Again, I'm not an R expert. We have some R experts over here. I know how to move around it, but I don't really like it as a language. It's because R has, you know, a lot of stuff already in there, and as we're going to see, it's not really that great. You'll see that most of the stuff, some of the stuff works, some of the stuff don't work. Python doesn't have, you know, this nice distributed stuff that we can get for free from R with R Hadoop. And yeah, I use SciPy, for example. You can, I mean, we have to come to a common language. So were you able to run the other summary, which is just one column?
Well, there's nothing to summarize. It's just text. But I do have it now. I put it into Excel and then saved the Excel and then imported it.
As a CSV, did it work? It might be possible because, and that's why I asked everybody if possible to use like Linux or Ubuntu, because there are all these things that they might work on one machine, they don't work on the other. And unless you are, you know, kind of like computer savvy and you know how to go around all these little tricks, then we're going to have this problem that we're not going to be in sync. Because, you know, we are about I don't know, there is 1, 2, 3, 4, and another 8, 12 people going. We're supposed to be more. So have you gone to? Okay, so are we? Does anybody finish with the summaries? Okay, so can we move to the next one, which is run your first linear regression? Yeah, you can remove it just to show you, but you can reload them. Yeah, use a small. I mean, you can try the big one, but you can try the big one, but you're gonna fail. I can see that some of you have probably smaller laptops, so yeah, there's not enough RAM. So first of all, you know, probably for your machine, like even you said you couldn't even load it, so you don't have enough RAM. I think it uses about 2 gigabytes or 3 gigabytes to around 3 times the memory. Yes. And then even if you're able to load it, for example, this is 8 gigabytes, it uses, you can load it. Then when it runs regression, the intermediate computations explode the memory. Okay, so are we ready to run our first regression? So the command that you see over there as attach basically makes your data global, so you can access them without this dollar string. You saw before that if you wanted to access an attribute of the data frame, you have to put this dollar sign. So when you say attach, then they become global variables. And so were we able to run it? Yeah. So you see something called summary. So basically when you run the model, when you say my model is this, it starts computing several things. So what do you see when you see summary? What are the things like? So let's start. So let's take. So first of all, do we know why we're expecting coefficients? What coefficients are? Is everybody familiar with the concept of linear regression? So we're taking the carrier delay. In this particular one, we use the carrier, but you can use the arrival delay. Okay, so now that we run regression, let's see, like first you kill, then you ask questions. That's kind of the approach we're getting here. So the idea is the following, and let me bring the board closer. And we're also going to write it for the remote students. Okay, if I can have your attention. The linear model is trying to predict y out of x1, x2, x3, and so on. Okay, so y is what we're trying to do over here is we're trying to, let's say that we are FAA, and we're trying to predict delays because we want to make a website that predicts delays, okay? So this is the delay of arrival, and these are several factors. You can put the weather, that we don't have it over there. We have the origin city, where the flight starts from, and the destination city. Okay, sorry. We also have the distance and some other parameters. Now, what is very important, so the question is that why are we doing regression now? When you're doing regression, when you're doing modeling, you're doing that for two reasons. One is for predictive power. So basically all I care, and I don't know, probably you can see our board. Let me also write it on. This is one of the problems I haven't solved, having a board for remote and on-site students. So basically say y equals a1 times x1 times a2 x2 plus A3 X3 and so on. So the question is, when you're doing modeling, what are you trying to achieve? The first one is that I want very high accuracy at predicting my delays. So if we were, for example, a big consulting company and we wanted to optimize our time, where you have people flying all the time, you want a model that predicts very accurately the flight delay, so you can schedule accordingly. And you don't care why the flight's delay. All you need is one value. What is my delay going to be? But there is also the other aspect of modeling, which is I don't really care that much about what I'm predicting, but I care more about explaining why I'm doing that. Why? So, for example, we can put a bunch of factors in our linear model, but we don't care how accurate our prediction is, but we care which factors are important. So we give more strength and more value in interpretability of the model rather than the precision. And we're actually going to see that it's kind of like a golden rule in machine learning. If you want your model to be very interpretable, then you're losing in prediction. Now, if you care only about prediction, then you can give up interpretability. And we're going to see that a lot of models, you can't really tell why things are happening. And that's also real life. In real life, the fact that if I ask you why do you think that this is drawers and bookshelves, you can start giving reasons, but when you are thinking about that, some complex things happen in your brain. You don't know why, you just know. We can't have a mathematical model of the brain and say, okay, it's this neuron contacting the other. It's too complicated. So now that we did that, let's get into the values. So you got it right here. You see that, so first of all, the values that you see are the coefficients, okay? The coefficients are telling us how much dependency we have from, like if it says that it's 5 times the distance, then it means that it's analogous to the distance. Now, as you notice, what is the sign of the distance? Let's check what's the factor, the distance factor. Yeah, it should be close to the end. Do you notice that it's negative?
Yeah,
so the negative means I think it's sort of intuitive. We are looking at the arrival delay. Actually, here we're seeing the carrier delay, but they're more or less the same. So let me see if it's on the next. So first of all, you see over there that if you go all the way down, distance here, it says, haven't you put the distance somewhere in your model? Oh, sorry. Can you?
We go up here.
Mm-hmm.
Yeah, I put the distance in the. That's right?
Yeah, you put the distance. Can you find it somewhere? I see other people have it. Distance. Okay.
Oh, yeah.
Yeah, so you saw the distance. So let's see if we can explain that, if we can understand that. The distance has a negative factor. It means that the longer the flight is, the less likely there's going to be a delay. Let's think about that. Typically, all of you have traveled with airplane. What happens is that we have a delay in the departure, and typically the pilot has time to, recoup that time during the flight. If it's like a flight that it's 2 hours and we already have 1 hour delay, like it's impossible, for example, to fly from here to New York in 1 hour. You can fly in 1.5, maybe 1 and 20 minutes. Now, if you're flying from here to, Tokyo, and there is an hour delay because the trip is like 12 hours, and there is great chance that he can take advantage of the streams and blah, blah, blah. So he has more time to speed it up. So that kind of like... Yes, I think, but here what's important is that because we don't measure the percentage, like the relative delay, what we measure is the absolute delay. But the idea is that you have more time. Just go to the next one, which says understanding the R output. And basically, you just have to run the same model, but instead of the carrier delay, I'm using the arrival delay. So rerun that model with the arrival delay. Were you able to? Okay. Now, you're getting obviously a different, a little bit different data, but that's fine. Now, you see something called, like, some stars next to your, okay, so what does these stars mean? So it's the significance. So you see, for example, that distance, day of the month, and day of the week are significant, okay? So let's try to understand that. The number you are getting there, like this coefficient, every number in statistics has a confidence. Is everybody with me? Do you have any problems running it? Just finish it because I think that's important to pay attention. So when we estimate a number in statistics, a number on its own says nothing. If I tell you that I'm 35, so somebody comes and tells you, I think Nick is 35, and somebody comes and tells you, I think Nick is 36. Who are you going to believe? You're going to believe the one who says, I think he's 35 plus minus 2, and the other guy says, I think he's 36 plus minus 10. The truth is I'm 36. But the fact that he's giving you a confidence around that, which is pretty wide, it's not a good thing. That's what the confidence is for the value. So what you see over there, when it says the distance is -3, this -3 is actually a Gaussian distribution. Does anybody know what a Gaussian distribution is? The normal curve. So first of all, we didn't say that, but linear regression has a lot of assumptions behind. Like when you're going to apply linear regression, you assume that your data, are independent, Gaussianly distributed. There's like 6 or 7 conditions. In reality, though, we don't care. We even use linear regression with success, even for data that they're not Gaussian. So basically, what that means is that we're getting a value and we say that it's -0.3, but in reality it can be anywhere between here. Okay, so you in the Gaussian, so basically it can be even -100, but that gives you a probability. If you go to -100, the probability of that being -100 is very, very, very small. Okay, now I want you to understand confidence intervals in a more practical way. So let's say that we lived if the theory of parallel universes is right, it means that we have infinite universes where we have the same flight schedule going on, obviously with different delays. So if we were able to play this scenario or flight delays 1,000 times, and we were running regression, we would get different estimates of the distance factor. And because we can't really live parallel universes, what we would do is we take a subsample out of our data and we'll fit a regression model. Then we'll take a different subsample. So basically, you do the same process again and again and again and again and again. Now, your confidence interval will be, okay, we ran it 1,000 times. On the average was 0.3, and the maximum we saw was 5, and the minimum was -5. Okay? And this is called the bootstrap approach. So here in regression, we don't have to run it several times because we make the assumption that we know the distribution. Like the distribution could have been something like that. Like if we were running it, it could have been something like this. Let me also plot it for the...
You're saying we're not running them all. When you're saying we're running them all the time, do you mean like running a simulation to discover where the actual true mean lies?
Yes, that's exactly. Well, it depends. If you're, we don't have to do that because we trust that the distribution is Gaussian.
So
in other models, so before I finish, like you could run the same thing with different other nonlinear models where you don't know what the distribution of your estimates is going to be. So what I was saying, and let me plot it here for the remote students. Okay, so I'm saying that the estimate, oops, sorry, not good at straight line. And I just see we have Vijay, who's a senior statistician, and he can correct us if we're making any mistakes here. So this is might be minus 0.3, and that's a Gaussian distribution, which means that if somebody was telling you that what is the probability of the actual value of distance being minus 100, that would be a very, very, very small probability, almost zero. And the same thing from the other side. Okay, now what I was saying is that we're making the assumption that the data is Gaussian, but it might have been the case where, as we're running an experiment, we will get a different distribution, something like that. So you'll say that most of the time it was minus 0.3, but then we also saw some values going up and down. That could have been like a histogram. We will have to bin that, the way we estimate that. I'm becoming better and better with this tablet. Okay? And so on. Now, let's go to something what is really important when you are, yes, when we are working with regression, there's two things we really need to be careful about, which is the confidence intervals and the p-values. The p-values is the last column. So the last column, basically, what it says, 0. So the p-values are telling you what is the probability of, your estimate being outside of, I think it's 6 sigmas or 3 sigmas, whatever is 95%. Is it 2? No, it's not. I think it's 95%. Doesn't matter. I can't remember. Maybe Vijay can. When I see we got more people joining right now. So basically, all you have to remember is that the smaller the p-value is, the more, yes, the more significant it is. The more confident you are about that. Then there is this command called confident intervals. If you want to run that, the conf int. So basically, it means that this Gaussian is very, very, very tight, very thin.
Yeah.
Yes.
Meetings should be helpful for the things to be done. And the meetings the reason for meetings should help the things to be done, not make the things delay.
Excuse me? I am hearing somebody. Do you have a comment? Is anybody from the remote students wants to say something? Anybody? No?
I can't see what you're doing. I see you waving your hands and a whiteboard so far away I can't make anything out. And occasionally,
did you just join us?
Off here.
Mm-hmm.
On the big whiteboard on my screen, rarely I see some handwritten stuff.
So, did you just join the conference?
No, I've been struggling on from the beginning.
So, as I said, Mr. Vasquez, we are going through the wiki where we have the class assignments, and we're going one by one. So, if you go to the wiki,
Aha.
If you go to a meetup,
you mean you won't have lunch with us? Yeah. Okay.
So,
thank you for letting me know. We'll go to your favorite place anyway. I'm kidding.
So are you in the?
I'm kidding. We have no idea yet.
So can I help you? If you go to the meetup web pages in the class wiki.
Okay, I found the meetup page.
The pages, and it says something assignments.
I've seen it before.
I think it's Google's new function, right?
So if you go to the meetup pages,
I know what you're talking about. I just have to hunt around until I find it.
Are you in sync? So if you go lessons, overview, and assignments, lesson 1, we are in number 5.
Trusting your results.
Yes.
Okay, I haven't found the wiki yet, unless this is the wiki.
So if you go to the meetup, it says pages. In the meetup, the banner says pages.
This is the thing that says, here are the goals, install R, load the airline, like that.
So just go to the meetup webpage and says pages.
Pages.
Pages, and then it says learning machine learning by example. This is the wiki that contains. This is the typo there. All the class resources. And you go. The third bullet from the bottom is lessons, overview, and assignments.
Lesson 1, presumably.
And then you go lesson 1. And we've been going from 1, and we are at number 5 right now.
Okay, I've been trying to do everything from the whiteboard that has this, blank whiteboard and this.
You guys will have fun.
Okay.
So I think we're making a little progress here now.
You're making some progress. And I believe you can always the session will be recorded. You can go back and play, replay it, or you can just go on your own through the 4 previous ones and do it. So let's see what do we have here. So do we understand the confidence? So what do you get in the confidence intervals?
I believe if I say model, it's giving the range. I presume this is the range. This is brief parameter.
Okay, hi. Just a second, we got. Yes, just grab a chair from either the meeting room or from here. Connect to the network, and that's fine. Can happen. So.
Is that what this is? So here's a parameter, and here's
2.5% and 95%, 97.5. So that's the probability, that's like the probability of the value being less than what you see over there, 7.9, is 97%. So there's still a 2.5% probability that this can be out of this bound. Okay, and it's Gaussian. Theoretically, it can be, infinite.
So is that the actual interval? So between, for instance, for origin ABQ, it's between -6 to 16? Is that the actual, is that the width of the
No, it's actually whatever is the value, what you got as the coefficient, plus minus this thing. But this is, so this is, you know, I think the first one goes with a 2.7. It's like an arrow value, and the other is 97. Okay. Now, there's something that you probably haven't noticed, which is how many factors did you put in your regression? Like when you write your model, formula equals, you know, arrival delay depends on. So it's 6. Why did you get 100 and like 200? How many did you get over there? You got a lot of factors. You only put 6 over here. Exactly. So we're actually having categorical variables. So what happens is that when we have numbers, you know, each number is a column. But if you have, like here, we have 199 cities. So basically what R is going to do, it's going to create for every categorical variable 129 minus 1 columns. Okay? So let me also write it over here. So for every categorical variable, R is going to create utilities. Okay, easy to delete this thing. So for every value, for example, if he wants to represent Atlanta, I will put a 1 in the first column and then 0 on every.
Sample is being created. I'll send you tomorrow.
Now, if you want to represent JFK, I will put 0 in the first and then 1 in the second column and so on. Okay, do you understand? It's a binary representation. So basically, you have 129 different cities. So in theory, you could just make 129 columns, and if the city appears as origin, you just flip the 0 to 1. Now, it doesn't use 129, it uses 128 because it picks. Like one of the cities can be all zeros. Okay? So you understand that. Like you can represent Atlanta as all zeros, and then every other city by just putting 1 on every column. And it's very important, if you R does this automatically for you, if you make 129 instead of 128, then you create rank deficiencies in the design matrix, as they call it, that makes things go really bad and ugly. Transform this categorical cell and then give it to the R. So how would you transform this to? I'm coming closer to the microphone.
For example, imagine that it was just a couple of them. If there was only 2 cities, we give one city 0, the other 1, and can we do like 0, 1, 2, 3 to all the cities?
Okay, keep that in mind. No, we can't do that, and I'll explain why. But that's a good point. So for those of you who didn't ask this, why should we, you know, because the cities were given with codes, ATL, JFK, blah, blah, blah. He says, why don't we just give like Atlanta number 1, JFK number 2, you know, whatever, number 3. So we can't do that. And we'll discuss that in the end, why we cannot do that. Now, did you also notice which city, like, seems to be very significant in your results? So it has a lot of stars. Could you explain how to read the model result? It's JFK, one of them. I don't know which city is MGM, but okay, so we got a question. Okay, Jacob. So I think, and I realized as I was saying, that I created a misunderstanding. So the F statistic or the P statistic or the T value, this is what defines the significance. And when I say significance, I should have been more careful about that, and I'm glad you asked that. It means that the number is acceptable. In what sense? Like there's always this null hypothesis, which is, what if this number was 0? What if that doesn't really depend on, this particular variable? That's what and I think accidentally I also got, it's been a long day for me. I haven't slept during the night. I got confused. The p-value gives you the confidence that the coefficient you found is not 0. That it really exists. Your variable really depends. Okay, and you can either use F statistic or the p-value, or P statistics, the p-values. The p-values, are more generic. You can have a p-test for any model. So basically, where your p-value is close to 0, it means that you can reject the null hypothesis. And I'm glad you asked this question, because when we build a regression model, we throw a lot of factors, and it's really a problem if the model doesn't really depend on that factor. Which we're going to see that later on, how we do that. Does that answer your question? If you want to read more, in the suggested reading of Lesson 1, you can go to Hasty and TBC Rani's book, which is available online. And I think it's this book over here that kind of explains things more accurately. We don't really have it's chapter 3 in the old book, in the first edition that I have over here. It's page 41. Okay, so I'm glad. That's kind of like the idea of the course. We will try to explain things in an intuitive way, and if people want to, so that's exactly what you're talking about, like the F statistics. I'll put it here. Want to go deeper on that, then I'll be happy to discuss it with you in private if you want, later after the class, if you have questions. Okay, so now we understood, why we're getting these extra regressors, although we put 6 and we get 200 ones. Now, let's try to get to the next. So the way that R works right now, it gives you, it can drop, gives you a p-value or a significance for, you see that some cities weren't significant. Okay. Now, unfortunately, so here's the thing: when you run regression, the fact that you're getting some p-values and some F statistics, you can't just say that it depends on that, it doesn't depend on the other. Okay, that's not as simple. Like, we can do, as we call, model selection by just ignoring things that they have high p-values or low p-values or F statistics. Basically, that gives you an intuition. Like, you will have to remove some of the values and rerun your regression, and you see what's happening. It's not an easy problem. It might be the case that two variables share the same information, and one appears to be significant, and the other appears to be non-significant. Okay. Now, I want to make something very clear, which is, you might have heard that correlation doesn't mean causality. There's this famous example about ice creams and crime rates. It turns out that when the ice cream sales go high, the crime rate goes high. And if you knew it. So if you think that the best thing the police has to do is ban the ice creams or to avoid crime, it would be silly. The reason is that they both depend on the temperature. When the temperature goes high, people tend to buy ice creams, and people tend to go crazy. So if you were running a model where you had crime rates and ice creams, basically these two factors share the same information. You shouldn't have to. It's very easy, to take random variables and throw them in the regression model and see some importance over there. regression doesn't really solve all the problems of the planet. There has to be some logic around that.
So it's good for predicting, but it's not necessarily good for truly understanding real system dynamics.
Let me put it that way. You have to be careful about that. You have to be careful. So we're going actually to the statisticians always debate, like Lauren, who sits over here, who's the chief statistician for Predictix, who, by the way, would like to thank for, I forgot, LogicLogs and Predictix are paying for the space, all the equipment we're having, and probably they're going to pay for the cloud time to use our Hadoop, giving us, you can also have soft drinks if you want to go to the kitchen for free. So we're moving to the next, it's number 6 or 7. The effect of collinearities. Okay, yes. Mm-hmm. Yeah.
Everything will tell you is significant. There's nothing that can, like maybe the p-value or.
No, I will tell you, because it does carry all the information about the weather. It's not going to be able to discriminate. So can we go to number like the effect of collinearities? So this dependence is also called collinearity because you can say that since ice cream sale depends on temperature. Crime rate also depends on temperature. You can say that that's exactly what we say, that there's a linear combination between crime rate and an ice cream sale. So if you're putting this thing, so the idea is that collinearities means that you have two factors that they carry the same information. Okay, so for example, what we do in the next number 7, in number 7, we create an extra variable which is called my distance, which is 3 times the distance plus the day of the month. So basically, it carries 2, information from that we already know. So start running this example.
What will be the difference between saying things are collinear and the cost of 4 that are just correlated? There's definite relationships.
So basically,
say they're the same thing.
So they're not the same thing over here. For example, my distance and distance are not the same thing because one carries some information plus something else. Obviously, these things are correlated. If you take their correlation, they're actually going to be positively correlated because we multiplied them with a positive number. If I put it in -1, so if we say it will be. So let's say, to put it that way, if A is 3 times X, then they are completely correlated. If you run the correlation coefficient will be 1. If it's 3 times this plus something else, it will be high, but not 1. Will still be some correlation. So correlation is not yes or no, it's a number. Again, I wanted to stress that machine learning is not really about regression. And as we're going to see as we progress in this class, that we're going to use more generic models that they don't make assumptions about the data. They run at a great scale, and they produce very good results because statistics existed before, and we knew about it. And it was all about that, measuring the distributions, being able to characterize them, derive mathematical models about them. So it requires a lot of mathematical ability and analytical skills. And regression is not my favorite tool, and I'm not even an expert in regression. There's other people in this company and from what I see in our audience, like DJ, that have experience working on that for many years. But it's, definitely a popular tool, and the goal of this lab session over here is that, if you have a predictive problem and you want to try something and you wanted to open R and start doing some work, you want to kind of know how to interpret things and where to look. So did you run the So you see, for example, that things start becoming a little bit ugly. For example, my distance now is something very, very statistically significant. Now, the day of the month actually disappeared. You see, not available, and this is because I suspect that R, as it runs the problem, goes into some rank deficiencies, and it says, I don't know what to do this thing. It's completely useless for me. And then if you run the next one, now if you run I just have it for comparison. If you run it correctly, you see that the values are completely different. Okay. Now, I wanted to mention something else. Another output from R that we didn't really pay that much attention is the residual. Which, does anybody know what the residual is? Exactly. So if the residual error is very high, it means that our predictions are very far away from reality. And I want to make something very clear. Now, we train our regression based on this observation, and the residual error is like the training error. It's, if we were trying to predict what we already know, how far we're going to be. There is something else called live-on-out cross-validation that we're going to discuss later, okay, which is a different way of evaluating the model. So basically, we run into a problem. We put two factors that, and actually we might have some other factors that, like day of the month and day of the week, might be correlated to. We're going to discuss it in the end. So we're not really buying that model. Like, this model is not a very accurate one, and it has problems, as we're going to see later. So let's go to number 8. Which says, remove redundant components with stepwise regression. Now, what is stepwise regression? Doing model selection is, let me take a look at it. Okay. So doing model selection is an NP-hard problem, which means from the N components or K components, pick the P ones that they model the problem, exactly. They are the most important ones, okay? Pick the P most important ones. Now, so we have to try all possible combinations and find the one that gives us the best error. But we can't do that, and we use the greedy approach, which basically is, okay, imagine that we can only use one factor. So we run a regression of arrival delay versus the 6 that we have, okay? And we find that in this particular case, destination or distance or destination gives us the minimum error. Okay, so basically, if you could pick only one parameter to put in your regression, it's better to put destination, because that seems to be the most important. So we say it's fine. We know destination is important. Now, the next step is, now that we have destination, let's add another component. Okay, so we try whatever is left. Origin, distance, blah, blah, blah. And we see that from all this, it's about n squared, but it's much better than, the factorial, whatever it is, exponential with, I think it's factorial with, all possible combinations. So it's exponential. Yeah. Yeah. The order doesn't matter now. So basically, it's a greedy algorithm. Like, stepwise regression is a greedy algorithm where you start with something and you keep adding whatever increases your error. Now, you can do the opposite. Now, you can do the backward, where say I start with everything and I start removing one by one and see which one, reduces, contributes less. Now, and there is something else called forward-backward, but it's fine. You can read more about it. It goes beyond the scope of this course. It will hurt you. That's exactly the problem, like you saw before. So here it's not that much about accuracy, because the more that you are throwing into your model, the better accuracy you are getting. Now, but in terms of, first of all, let me put it that way. first of all, your model might become unstable, because if you, for example, have factors that are collinear, you might actually see the model becoming unstable and giving you bad values. Like you have rank deficiencies, the linear algebra doesn't work very well. And there is a problem over there. For example, if you add the same column twice, the regression cannot decide. If let's say we knew that the true factor was 5, and now I'm putting the same factor twice. Shall I put 3 here and 2 here, 1 here and 4 there? So it cannot decide, let me put it that way. And it starts acting crazy. Okay? So I think in this particular case, the way we did it, I was able to detect and completely throw away the my distance. Okay? But things are not always like that. Not nice like that. So you kind of do it for the stability of your model, and obviously removing factors that they are not significant. As you can see, so start running stepwise regression. Did you run it? Were you able to run? So you see how it starts and it keeps adding, and you can see some factors. I think the AIC score and the residual. What do you see? What does it?
Taking forever to complete the.
Okay, so it's taking long, because it has to recompute the regression again and again and again. It's a slow method. Now, so you're doing the forwards. Now, although forward and backward are more or less the same methods, there is a big difference. Like if I was giving you, can anybody see what's the difference between running forward and backward in practice? Like, is there a case where you say, well, I would prefer to run forward rather than backwards? Okay. It's not actually the confidence interval, it's something else. It's either the AIC score or the residual, whatever, or the number of factors. So you're right. If you have a regression that has too many regressors, let's say 10, 20,000, we are expecting that most of them are going to be, dependent. So if you start with 10,000 and start removing, you have to run most of your time big regressions. But if you start from 0 and you keep adding, because the problem is that as your model grows, the regression becomes slower. Because the complexity of regression is n, where n is the number of your observations, times p squared, where p is the number of regressors you have. So it grows quadratically with the number of regressors. So you have to be careful. So has anybody finished with the regression? With stepwise? Okay.
How many outputs? What is the amount of output they're supposed to print?
Okay, so that's a good question. How many outputs is it supposed to? So there's something called the AIC score where you can read more about it, which basically, as we said before, the residual, like the accuracy of your prediction. Okay, your attention a little bit here, and I'll write it for the remote students. So your accuracy, starts very high, and as you keep adding factors, it starts dropping. Okay, and it goes whatever close to 0. So it's kind of like heuristic. You will see that, after adding one factor, I have a very big drop. So once I have a very big drop, there's no point in continuing. There's something else called the AIC score, which, can be something like that. So the AIC score, let me plot that for the students. So I was just saying that in the stepwise regression, this is the residual error, and as you start from here, then you go there. As you keep adding factors, it's going down, and there is a point where there's a big gap, and that's where you decide to stop. Now, when you look at the AIC score, the AIC score can behave whatever it wants. But there are cases where there is a minimum. Basically, that's the optimal model here. But it's not always guaranteed that we will have a. In this example, we see that it's going down monotonically. If I'm right, okay, if I remember correctly. So the AIC score kind of like penalizes that. Okay, I like it has something that it's proportional to the residual error. So the less residual error you have, the better the model is. But it has also a penalty factor of the complexity of your model, which is the number of factors you're putting. And that's the cornerstone of machine learning. And generally speaking, in machine learning, you want something that predicts well, but it's also very simple. It's called the Occam's razor. So, for example, forget about linear regression. If we wanted to model our data correctly, we could just put a lookup table and say, if starts from Atlanta, goes to New York, and the distance is in this small interval, blah, blah, then the delay is that. So we can have, if we want zero error, we can achieve zero error by just making a lookup table, an if then else, a big if then else statement. But the problem of that model is that it doesn't generalize. It's very complex. So we want something that, kind of like describes the data, but it's as simple as possible. And that's where the cross-validation comes. So in the cross-validation, so let me give you an example before I go to the cross-validation. Okay, so in a sense, when you have linear regression in 2 dimensions and you have a cloud of points, you fit a very simple model and it has an error. You could have as well fitted something like that. It's a curve that passes between all the points, but it doesn't generalize, doesn't give you any information. Okay, and let me plot that here too. So I was just saying that in linear regression, you might have seen that in your undergrad. These are your points. And you can fit either a straight line, didn't do it very well, or you can fit a very complicated model that passes through the points. But it doesn't give you any information. Sorry. It's really difficult to delete. Okay, we can just do a clear all here. Okay. So in cross-validation, basically what we're doing is that we take a sample out of our training sets, we train our data, and then we see how does it behave in the data that it hasn't seen before. This is called the generalization. And wherever you're having a machine learning problem, that's like a very, very common technique, because you also have to tune some parameters. You keep some data out and say, okay, my model hasn't seen them before. How does it behave? And this is what really, the training error doesn't really mean that much if you're going to do a predictive task. Okay, so talking about that, in regression, we started in this particular model where we have 260 regressors. Now, our goal is that how many can we really set to zero? So apart from the collinearity thing, now imagine that we don't really have collinearities. Everything is independent. We still want to set things to zero because that will make the model more simple and it will generalize better. That's kind of our, even most of you are, or some of you are software engineers, and the cornerstone of all software engineering is the abstraction. So I don't have to have a million special cases. Can I have a general thing which is simple and can describe everything? And in other parts of life and science. So that's what model selection is trying to achieve. And that's why, we kind of cared about the p-values. In statistics, you always have this null hypothesis. You say something, says, what if it's not significant? It's zero. It doesn't exist. And it's good to have them. Okay, so let's go to number 9 right now. Let's see other methods that can... So the AIC is a score that describes the simplicity of the model and the accuracy. But you know, there are several versions of AIC, like how much there are weights, how much you penalize the complexity of the model, and how much you value the accuracy of your model. So probably then you have to choose the minimum. So actually, did you notice that as you were running the stepwise regression that I think magically one of the regressors disappeared completely from the, I think my distance, or which one was a month, day of month disappeared, just because it identified that there's no improvement at all with that, so it completely eliminated it. Okay. No, there's something else. As you run it, you see it. Sorry, I don't have it. So it's my distance. So you see, for example, that the day of month magically in the last step, you know, although it's scored seconds, if you see, you know, where it says, so by the way that it plots at every step, it's what is important, like what it contributes more. So it always picks whatever it's first on the list. So you see where you have distance that's first on the list, and then you have day of month. Like in the next model, day of month completely disappears. It doesn't even participate anymore because of this linear dependency. Yes.
So you look at the model, right? Say
Mm-hmm.
the only difference between it is day of week. You take day of week out. Oh, yeah. Sorry. Okay. Yeah.
Okay. So let's go to. There's another method called Reed's regression. So Reed's regression does the following. Okay. You remember this problem that I talked about? If you add the same column twice, where the model cannot decide where should I put more value, like should I say 4 this and 1 the other, 2, 1 and 3 the other. So it says, I want you to shrink the coefficients as much as you can. So it adds a penalty in your objective function. And it says, I want you to pick the model that not only predicts well, but has the minimum. So it tries to push the values to 0. Because what did I say before? Our goal is to get as many zeros as we can, or like values very close to 0. Okay. So if you run, you're able to run Reed's regression. Anybody? Now there is a problem with Reed's regression which we had in the previous class. If you try with a different data set, apparently this implementation of Reed's regression is not really that great. And if you're having missing values, or if you have, so here's the problem. I mean, start running it, and once you're done, I'll explain one of the problems that you might come up. So it's really sad that we have mainly students in this, and in the other on Fridays we have the engineers. It seems to me that I see that we didn't have a lot of people today. We might have to merge the classes and bring together. It's also going to be good for you because there's companies hiring. We're already having somebody from the first class being interviewed now. So
yeah, I work in a software company.
oh yeah, you went here in the introduction. So basically, yeah, I mean, feel free to write more on your profile and meet up, so that people can. So were you able to run Reed's regression? I haven't talked to you, but were you able to follow up to catch up with it? Okay. Okay. Maybe you can tell us more about R, because I always, as I said before, I don't like it as a language. I don't think I know it that well. It has all these shortcuts. Yeah. So you have this penalty factor, this lambda in Reed's regression, which kind of controls how much you put things to 0. And the way that you tune that, the way that you would tune that is that you would hold out a set, again, so ridge regression will have worse accuracy prediction error in the training data than normal regression, but it will generalize better. So what you're doing is that you take subsamples out, or you take a sample out, you train your ridge regression with a particular lambda, then you test. Then you change your lambda, so you sweep your lambda between 100 values, 10 values, as much as you can. And this is really the beauty of R Hadoop over here, because R Hadoop will do that distributedly. If you have to run this regression 1,000 times, you can do it with R Hadoop. You use the lapply or sapply command. And when I talked before about deriving confidence bounds, you have this power right now running the same thing several times. So so you have to experiment with different values of lambda, cross-validate over different values of lambda, and the one that gives you the better generalization error on your test data, that's the one you keep. Now, we're actually getting close to, I have to leave 6 up and I want to leave 10 minutes. Now, another method, yes, before we go to another method, we kind of noticed with different students that for different samples, the ridge regression was crashing. And thanks to a student from the previous, from 1A, A class, previous Friday, we found out that, you got categorical variables, okay? So you have 129 cities or a year. Now, what happens when you take a subsample? It's possible that, you get only one category. Okay, so we took the first 10,000 lines of this 2007 file, and it just happened that the entries we got had only as an origin city Atlanta. So basically, you're having a categorical variable with one category. It doesn't make sense. Zero predictability power. Why do you need that? So what happens is that replaced us with zeros, and this zero thing, completely zero column, creates some normalization. If you go through, I went through the code and I saw that it actually tries to do a mean normalization with zero, so it gets garbage because it divides everything by zero. So you have to be careful when you take subsamples. You might run into problems like that, like your variables are undersampled, or maybe you have one category and then it can create problems.
These are things. These are workarounds because R is doing automatically. But if we programmed it using Python and just did it in your algebra, then we would do this, right?
Believe me, if you were doing that, because I've done this in C++, like for example, let's say you were doing that, right now you have 128 columns, and I told you if you have 129 cities, it has to be 128. Now, if you subsample and your categories are actually 100, and you have a lot of zero columns, you have to manually remove them. So you have to be careful to remove zero. Numerical algebra doesn't like zero rows or zero columns. Maybe your software will take, I think MATLAB handles these things automatically, will detect that, but not, if you were doing on your own, you have to be careful. Again, now we're going to the next one. Unfortunately, we won't be able to do it. So lasso is a more fancy method. So now we're still putting a penalty on the, okay. All right, we have VJ, and I was expecting this question here about VIF. Okay, I think it's, I see from the remote students, because my chat window is kind of small and my eyes cannot catch it, it's better if you post it on the whiteboard because it's bigger. So we had 2 questions. So what is doing with Lambda and the ridge regression? I think I kind of explained that. Lambda puts an extra penalty.
Hi, Ted is really having an emotional breakdown. We need to talk to him on a phone that doesn't cut out all the time.
Excuse me. So you're having breaks from your. You can hear us well.
Okay, this is your class, I guess. Hello.
Yeah.
Yes. This is the class.
Oh, okay.
The instructor's trying to talk to you.
Oh, okay. I will get back on the other phone then.
Yeah, you can always join by phone. There's a number you can call. So I don't know who was right now, but it was anyway. So maybe it was Darson. So okay, yes. So in ridge regression, again, it's this lambda is the factor that says how much we should really try to push the values close to zero. And basically, the higher lambda you have, the simpler model. It kind of controls the complexity of your model. Okay, how simple your model is going to be. And now Vijay has a great kind of like comment over here. There is something else which, unfortunately, I probably added in the wiki. Unfortunately, we only have 2 hours to talk about. It's a variance inflation factor, which actually R has has a package. Actually has a native function about that. So basically, in the VIF, what it does is, in order to detect collinearities, you take, forget about what you're trying to predict. Forget about your Y. You will take X and find out how well X can be predicted by the other factors. And then there is a formula over here where you compute, and it tells you, how significant your hypothesis. So you're making a hypothesis that actually X1 is a linear combination of all the others. Okay? So again, let me write the model over here. No, we had, okay. Y equals X1. So basically now you're saying, okay, forget about Y. I'm trying to predict X1 from, let's call that, I'll call that B. X2. So, and then I do the same. X2, maybe I should omit the piece, like from X1 plus X3, and so on. So basically, I'm making a hypothesis that my X1 is linearly dependent from the other two. I run the regression, and then there is a formula where you plug that in and it tells you how important or how significant if your hypothesis is true. And that's a very legitimate way to basically compute collinearities and throw them out of the model. Now, again, I think TB Sirani's book has the variance inflation factor here. If you want to read more about that, let me take a quick look. I know it works very well in practice, so I don't see it in this book, but you can just Google it on Wikipedia. There's an article over there about it. Okay. Vijay, feel free to intervene and talk more about it. Yeah, it's the car package. So it's the car package Vijay says that has the VIF. It's not it's not a native function. So Lasso, let me clear that. So Lasso, this method Lasso, what it does is it penalizes the values, the coefficients, but in a different way. So the ridge regression penalizes the L2 norm. Does anybody know what the L2 norm is? So Lasso will, let me write it over here, will try to add, it will add a penalty function like that. A1 square plus A2 square plus A3 square. This is like the Euclidean norm. Okay? Now, this is what ridge regression does. Let me... Actually, I can use multiple whiteboards. I didn't know about that. Maybe it will be a good idea for future classes for you to connect to WebEx only without audio, just the matrix, so I have to write everything once. I wouldn't really... so basically now Lasso does something else. It penalizes this thing. Now, since you are coming from, the students here are coming from the signal processing community where you know about compressive sensing. It's kind of like the same idea. It's called L1 regularization. So basically, let me write it over here. So ridge regression tries to minimize this. Lasso will penalize okay. Now, don't forget, lambda should always be positive. Never try a negative lambda. It will be a disaster. So the L1 norm has this magic advantage. And there are some very success and nice stories about that. I wish we had more time to talk about it. That automatically, so ridge regression will push values very, very close to 0, but maybe never 0. So L1 will really, really give you 0 values. Now, there's this package called LARS, and I tried to run it with an airline data set. There's something wrong with the data somewhere, a missing value. I don't know. It doesn't really run as I wanted, but I didn't have the time, and I knew we wouldn't have time to resolve it by now. And there's also something else, which is the next thing called grouped lasso. The grouped lasso, what it's going to do is that when you are having categorical variables, it will group all of them together, and either all of them are going to be 0, or you asked that before. You said, when you are, how do we assign a p-value to all categorical variables, or how do we reject them or accept them? Okay, so there are cases, for example, that with the airports, okay, it makes sense. Like we know we want to maybe drop some airports, say, okay, we don't care if it's flying to Athens, it's never going to have a delay. It's not really significant. We're not really having that many flights. Significant also comes from how many observations we see over there. Okay, so it might not make sense to, there it might make sense to drop some of the categories, but there are other cases where we need to keep either all of them or not. So grouped lasso will group them together. So there's a package called GRP lasso. I was very close to running it. Again, there is a problem with the way that it wants the data. All these are submitted packages. They're not very well maintained. And maybe I'm also doing something wrong, but if anybody wants to take a look at because I see we have some experienced users online, if they want to take a look at the wiki and fix the code over there and make it run, I'll be very grateful for their help. Besides, I knew that we wouldn't have the time to go all the way there, but it's good for you to know the existence of these packages and understand their value. Now, we said what we said, and I really followed the strategy, or I tried to wear your shoes. Like, I'm a software engineer. My boss gave me a problem that I think I can solve with regression. Let's start working from a book and, running around and asking about R and trying to fix things. But what we've done so far is completely wrong. Not completely. It has a flow, and it's actually, if you read, it's number 12, and we kind of made the mistake that you mentioned before. You asked before, why don't we take the cities and we just assign like city 1, number 1, city 2, number 2. You know what? We actually did that with day of the week and the day of the month. And this is creating a bias, actually. If you see the results, it will tell you that the more you travel, like if you travel towards the end of the month, it tends to have a delay. But that's completely not true. The problem is that, we gave more importance because we said that the last day of the month will be 31 and the first will be 1. We also said that Monday will be 1 and Sunday will be 7. To actually get the same result, if you travel on Sundays, you'll get more delays. That's not right. That's not true. And your representation is biased. Okay? So if somebody comes and says, let's change and assign number 1 to Thursday, then you will get completely different results. Different significances, different p-values. So there is definitely something wrong in your model. Like, you have to treat these days, these factors as categorical. But I thought that, and that would be your initial, like if you're trying to do modeling, you'll say, oh, okay, these are string code that's categorical. This is numbers, so that's numeric. That's not how it works. Okay, this is not how it works. You have to think: is this really categorical or not? There are some values like ordinal values. For example, if we had a score 1, 2, 3, 4, 5, like the temperature. The temperature that's not a categorical variable. It's a continuous variable. There's a difference. So that's called okay, temperature can be a numerical value, but you can have somebody scoring 1, 2, 3, 4, like Netflix. That's like an ordinal value. So it might be discrete, but the ordering matters. In the month, the ordering doesn't matter. That's what you have to think about. Now, there's a last point that I want to make, which is if you really want to enhance your models, you can add more nonlinear factors, okay? So they call that interactions. So you can take factors and take their multiplication. Okay, so for numerical values, the multiplication, like the distance and they call this interaction terms. So the distance and the temperature, for example, will be a numerical product. But if you take the origin times the destination, that's a categorical product. It's a Cartesian product. Okay, so basically, if you have 100 origins and 100 destinations, you're creating a new categorical variable that has 10,000, different categories. And that will improve your, actually, the accuracy of your model, because it makes sense to say, like, for example, maybe San Francisco is a fantastic airport, and it doesn't have delays, but the specific flight, San Francisco to New York, it's always delayed because, the weather is bad, or, that's like the time that arrives on JFK Airport, it's also where the international flights are living. So basically, right now, you're looking at your problem at a finer grain. You're not saying, okay, San Francisco, New York, treat them independently. You treat them at the same thing. Of course, in order to train a model like that, you will need many, many, many observations, because, first of all, although it sounds like, and I'm getting into computational stuff, although theoretically you have 10,000 possible pairs of destinations, in reality we know that the airports are not designed like that. The airports have a hub or star-like graph structure. We have hubs. We probably have LA, San Francisco, Salt Lake City, JFK, Atlanta, Ohio, whatever. It's about 10 or 20 cities that they connect with any other city, and very few. So obviously you can take that, like if you try the naive approach and you do it like that, so you take every possible interaction, then your matrix is going to explode. I don't think R is able to run 10,000 variables. Now, Revolution Analytics R, it probably can do that because it does a clever representation, so it doesn't store everything as double. It uses a sparse representation and so on. So it's almost 6 o'clock. I have to leave to pick up my daughters by 6. So do we have any questions?
Well, I noticed the lasso method brought up an error.
Yes.
Yeah, and also, so what would occur? I mean, even though the data we're modeling it linear, right? What would occur if we use a neural network to do that? I mean, wouldn't that solve what you're basically getting at?
So you're saying if our model is linear and we're using a neural network,
sure.
Basically.
The extra granular detail that you were.
So here's the thing: if your model is really linear and you're using something very complicated, you increase the complexity of the model. Okay. So if linear regression works well, I wouldn't use a neural network. Why? First of all, the linear regression has a unique solution. When you run it, you run once, twice, 10 times, you get the same thing. It's much faster. It's actually a convex problem, so it has a global optimum. We know that what we found. I take that back. The optimum is always the same. Now, for example, the ridge regression will always get you to the same solution. Linear regression, if you have instabilities or collinearities, will always give you the same optimum, the same minimum residual error, but different values. But in general, it's much more stable than a neural network. The neural network is what we call a non-convex problem. So every time you start, it will give you a different solution. Second thing is that the neural network will not give you, I suspect you're talking about the multi-layer neural network with non-linearities, not just a linear, because there's also a linear neural network. This will always, will not give you interpretability, and you probably have to run it several times to find out which is the global optimum, and you won't even be sure about that. So if now linear regression gives you horrible results, then yes, you switch to a neural network. So the bottom line is that we try from the simple and we move to the more complex because each of them has a specific advantage. Do we have any questions from the remote students? So I heard that some of you had a problem with the connection. See, some of you are joining through the phone, so probably, please write us some review or feedback. I can guarantee you that the last previous classes, remote students had a more horrible experience because we didn't have WebEx and this tablet and this good camera. The previous camera wasn't that great. So let's see how we can improve it.
I didn't find the WebEx very useful, but that once I got on to the correct website with the meetup, that was worth 50 of the WebEx.
Yes, I should have put that on the table because I didn't think. Again, it's an experimental course. We're starting. It's the first time that we're doing a meetup as a class. So yes, it's a good idea. I should put it on because I didn't think that some people might join late. Okay, so it's almost 6. Let's. So next week is Thanksgiving. So we're not going to have a class. So it's going to be after that, the week after. Okay. So enjoy the break. Oh, you come tomorrow? Yeah. Feel free to switch. Yeah, that's fine. That's fine. No, generally, again, there's in 2 hours. That's what we can do. Now, if you want to go back and rerun and also investigate, see other packages or experiment, learn the language. Unfortunately, we don't have the time to learn the language, so we kind of give you the minimum you need. And again, that's the whole concept. Towards the end of this series of courses, we want to be able to work on a real problem where, coming here will just be updating what we've done, trying new things. And it seems to me from tomorrow, I think we'll spend most of our time making sure that our Hadoop works and spend more time there. And again, some people that are experts, they would, or they don't want to learn more math. They would be more interested in spending the time on our Hadoop and setting up a cluster. Some other people would be more interested in, say, I don't really have that much big data. I don't really need Hadoop. I do care more about learning methods and what they do. So I have posted if you go to the class tomorrow, there's we're going to discuss. I haven't been able to enrich it to bring it in that form, go step by step. We'll see. I got other things to do too. Okay. So thank you again. Let's see how we stop this thing. Feel free to join tomorrow too, if you want. If we see that the participation goes down, we might merge the classes. Okay, thanks Vijay for the comment. So enjoy the weekend. Bye-bye.